Hello everyone, Aaron here, and welcome back to Leetcode. Today we are doing the delete the middle node of a linked list problem. You are given the head of a linked list. Delete the middle node and return the head of the modified linked list. The middle node of a linked list of size n is the floor of n divided by 2 node from the start using zero-based indexing, where floor denotes the largest integer less than or equal to x. For n equals 1, 2, 3, 4, and 5, the middle nodes are 0, 1, 1, 2, 2, respectively. So here we have a list of length 7, so that should give us a 3, 0, 1, 2, 3. That's all we need to remove, so we need to stop at the 2, wire around it, and we're done. All these behave the same way. Length 4, 0, 1, 2. Length 2, 0, 1. The number of nodes can be as low as 1, in which case we don't delete anything. The value can, well, we don't care what the value is. Okay. If you saw yesterday's video, you'll know I don't love these kind of problems, but at least this one isn't so bad. Like, deleting the middle element of a linked list is actually something you might want to do. You might have some data structure where, I don't know, it's increasing from both ends and you want to collapse the middle or something. I don't know. That's actually a legitimate problem. You still probably wouldn't use a linked list, but hey, at least it's not completely stupid. Right, so my immediate thoughts with this is we want to do a tortoise-and-hare style algorithm. So tortoise-and-hare algorithms are famously used for finding cycles and graphs, but they can be used on linked lists very nicely too, because basically you're going to have something that moves slowly, the tortoise, and you're going to have something that moves very quickly, the hare. And in particular, if the hare is moving twice as fast as the tortoise, by the time the hare reaches the end, the tortoise is halfway. And that's exactly what we want. So here, if the tortoise and the hare are both starting at position 0, in the next step, the tortoise is going to move to index 1, but the hare is going to jump all the way to index 2. The tortoise is then going to move to index 3, but the hare is going to move all the way to index 4. The tortoise is going to move to 3. The hare is going to move to 6. And then the hare is stuck, so we know we're in the right place for the tortoise to delete its node. So the easiest way to do this is probably to maintain a trailer, which tells us where the node should go. Where the tortoise just was. The other way to do it, and the reason I stumbled over my words is I was sort of thinking in my head, if we see the tortoise has somewhere to go, but if the hare does have somewhere to go, but after that the hare will have nowhere to go. So let's do the next one. Tortoise and hare are here. Tortoise goes here, hare goes here. The hare can't do the next step, so we want to remove. Okay, so that's the condition we need to check. Either the hare fails, can't get to its destination, or the hare can, but is then at the end of the list. I'm just running through all the edge cases on that. I think we're fine, apart from the case where it's of size 1. And the reason it fails at size 1 is, well, the hare can't get anywhere, but we can't even do anything with the tortoise. So I think there's going to be a Whatever. If head, I'm not in C, is none, return head. So here we've got tortoise is head, hare is equal to head. While true, what we want to do is we need to go if hare.next is not, well, that should never be the case. Hare.next.next is none, break. Elif hare.next.next.next is none. In fact, we'll just make this into an OR. Tortoise is tortoise.next. Hare is hare.next.next. Tortoise.next is tortoise.next.next. So this last line here is the actual deletion. So if we get to here and we see that the hare can't go any further, hang on, let me just check that. So we were here, tortoise, hare. The hare can't go. Next.next is none. So we're going to stop. That means the tortoise was looking here. Its next thing should actually just skip. And in either case, we want to return the head. The reason it asks us to return the head of the new linked list is almost certainly for... oh, hang on. No, let me finish that thought. Is because basically, if we're doing this in a functional language, something like OCaml, then we would want to use we wouldn't be able to mutate the list like this. We would need to create a whole new list. The reason I paused there was because basically, if it's of length 1, we actually want to return none because we want to delete the item in position 0. So I had my base case wrong. So that's just handling that special case. Now we know we're of length at least we're of length at least 2. This case here. So does this handle it? This is this and tortoise and hare are both looking here. The hare.next is none. So we break out tortoise.next is tortoise.next.next, so that's fine. Okay. I hope we're allowed to mutate the original list. Yeah, we must be able to return, modify the list. So, actually I'm going to leave that comment. Just move it down a little bit. So all right, just adding a little comment there just to say that we know the tortoise has ended up in the right place. So the tortoise moves slowly, the hare moves quickly, we end up finding the middle node. Let's do a quick check. This first one is usually just a typo check. What have I mucked up? Tortoise. I knew there was going to be a mistake. Should have just called it a turtle. I can spell turtle easier. Right, let's try all the test cases. Excellent, looking good. let's give it a single node and just check we're handling that test case correctly. We are. So our test cases handle 1, 2, even, odd. That's about all the cases we need to worry about. So let's submit it. See what happens. And perfect. That's exactly what we want to see. Not too tricky a problem. Was this an easy or a medium? This was a medium. Okay, that's all right. It's one of those ones that could go either way. If you've seen tortoise-and-hare algorithms before, not a hard problem. If you haven't or didn't think to apply it, this could be tricky, because let's go through what the immediately obvious solution is. The immediately obvious solution is to write a delete at index function and to write a length function. So the first takes the length, then you compute the middle index, and then that gives you the delete at, then you pass that on to your delete at index function. But the reason we don't want to do that is basically because that ends up being a, you repeat a lot of work. It's kind of like a Schmiel, the painter algorithm. I have a video with an animation that took me way too long to make on one of those. The idea is that you end up redoing a whole lot of work. This isn't quite a Schmiel the painter algorithm, actually. It's not quadratic. It's just wastefully linear. Because you walk the whole list to find its length, and then you walk the first half again to get back to the middle so you can delete the node. We don't need to walk it all the way and then again. We can just walk it halfway, effectively, in one go. The tortoise only ever gets halfway. The hare races all the way to the end, but we skip half the nodes when we do that. So this is n/2 nodes get looked at. Well, nah, we do actually need to look at everywhere. Quibbly, it's order n. And it's order n with much nicer constant factors than the all the length and then get halfway. Anyway, that's me rambling. It's a Friday. My brain is half fried. I think we all deserve a weekend. I do hope you all have a wonderful weekend. Like, comment, subscribe, all that good stuff. In particular, I'm really keen to hear ideas on what you'd like me to do. The videos that have done well recently are obviously the hard problem, so perhaps I should have a look at doing hards. And the APL one, surprisingly. That seems to be doing all right, maybe because there's not a lot of content on APL, but I'd be quite keen to make some more. So do let me know if that's what you want to see. That's it from me. Have a good weekend. I will see you next time. Bye.